Chapter 5, Number 27. A farm tractor tows a 3,300 kilogram trailer up a 14-degree incline with a steady speed of 2.9 meters per second. What force does the tractor exert on the trailer? So we'll, as almost always, begin with some sort of picture. So we have some sort of incline, and we have the trailer, which is just a box on wheels, and it's being pulled up the hill via some tractor. And most importantly of all of this, it's being pulled up the hill at a steady speed, which means no acceleration. So if we consider just the tractor, or just the trailer, and we say what forces act on the trailer, we would have the weight pulling directly downward, and we would have a normal force pointing out of the incline, and we have the trailer pulling up the incline. And these three things should add to zero. Here we're sort of assuming, well, I guess we're not assuming, I guess they told us we're going to ignore friction. So these are the three forces. Being a free body diagram, being a collection of forces, I can actually redraw them. So we'll have the tractor force going along the incline. We'll have the normal force pointing perpendicular to the incline, and I'm going to arrange this to be already in tip to tail. Over here it's in some weird diagram bit, but I want to put them in tip to tail, and when I do that, that means the final bit's going to have to be the gravitational force like that. And we know that this is, of course, a right angle. That has to be the case because the sum of the forces is MA, but A is 0. So the sum of the forces is 0. And three vectors add to 0 only if they make a triangle. They don't necessarily have to make a right triangle, but we do know that the normal force is always perpendicular to the incline, and therefore perpendicular to the incline, and therefore perpendicular to the force exerted by the tow bar, which is along the incline. Our last thing is going to be to try and get the angle of the incline into the triangle we have. And because my scale is not great, I'm just going to redraw it a little bit to make it. So there is our incline, and here is our gravitational force, which I'm choosing to accidentally sort of align with the incline, but that works out fine. And then here is the normal force, which goes perpendicular. And then here is the tension in the tow bar, which goes along. And although my drawing isn't particularly great, these are both right angles. And this is a right angle. So the angle that we were sort of given is the angle of the incline. And we can see that that's the complement to that angle. But then that angle is the complement to this angle. And the only way that could work is if this angle is theta. So therefore, going way back here, this angle was theta. All right. And so I'm going to get rid of I can keep a diagram in here for a bit. Create a little bit more space for myself over on the side here. Now we apply trig, and we say that the sine of any angle is the opposite side over the hypotenuse, but in our triangle, the opposite side is FT, and the hypotenuse is FG, and that tells us that FT is FG sine of the angle. So we have to take our 3,300 kilograms times 9.81 meters per second squared times sine of 14. Wow, that was terrible. Let's go over here and say that FT is FG sine theta, so it's the mass 3,300 kilograms times 9.81 meters per second squared times the sine of 14 degrees, which comes out to be 7,831 newtons, but we really only have, at best, 2 sig figs. So we should probably call this just 7 to 800 newtons. Notice something really kind of weird, but the actual speed never comes into the problem. The fact that it's 2.8 meters per second, irrelevant. The only thing that's relevant is that it is steady. It could be going 10 times as fast and it would still exert the same force.